All right, so today I'm going to require your absolute focus, absolute attention. You have to follow what I'm going to be saying step by step. And these coming weeks that we're entering will actually be one of your hardest weeks because we're starting to revise past papers. So as we solve these past papers together, you have to make sure, please watch these videos every day. Immediately after I send you this video in the night, try and study this video. I'll send you this same past paper. So once I send you the past paper in your book, I want you to be writing the questions exactly as they are. Write down the question. If there's a diagram, draw it. Use the video. Try and solve everything exactly the way I've solved it on actual paper. So we're going to, because I have to teach and explain the content of these questions. So I just told myself, all right, I'm going to focus on two papers. We're going to do Science Paper 1, 2020, which is the physics paper. It has got three sections. Then once we are done with this one, we're going to move on to Science Paper 2, which is the chemistry paper, which also has three sections. So in the exam, you're going to encounter a paper that looks like this. Online-based systems. The thing is stuck for a bit. Hold on. So in the exam, you're going to encounter something like this, which says Science Paper 1. This is Science Paper 1 2020, and the paper itself carries 85 marks. Ooh. All right. So the paper itself carries 85 marks. So if we can read through the instructions rather quickly, we're going to say, as you can see, there are three sections here. There's section A, B, and C. And you have to answer all questions in both section A and section B, but at least you get a break. Once you reach section C, you can answer or you can attempt any two questions. As you can see, section A, it consists of multiple choice questions, and you answer them by putting a cross on your answer. So you find something like this. So all question 1 to 20, you have to put a cross. So because of the nature of how we're going to be learning these things, we're going to take our time in terms of solving these papers because I have to explain. You're going to see what I mean when I say I have to explain. So we're going to do the first part. We're going to do question 1 to 10. Then I send you the video. You get your physics tuition book. You write everything word for word. The way I solve them, the way I solve these questions is the way you have to solve these questions also in your actual physics book. Make sure you watch this video over and over again. The preparation for your exam has begun, and science is not an easy paper, so you really have to be on top of your revision game, on top of your study game, on top of your understanding game. So are you ready?
Yes.
All right. So I can you see this paper clearly? Can you read everything clearly before I start?
Yes.
All right, okay. So question 1 is a question which has mathematics in nature. So let's read this question together properly. I'll read it, but I just want you to follow. Draw my highlighter. I like my green highlighter. So we're talking about significant figures here. So it says, how many significant figures are there in the number 0.050200 of 50200? Okay, so this digit here, in terms of significant figures, we have to know certain rules of significant figures. So the first rule that we're going to talk about is leading zeros, which is zeros at the beginning. So anyway, not this one. Let's start with whole digit numbers. So rules of significant figures. I want you to know about 3 or 5. So the first rule that you're going to know in terms of significant figures is that all whole number digits are significant. So whole numbers are significant, whole digits. So if I say I have a number like 44, for let's say 445, these are they are whole numbers. So this number here has got three significant figures. So whole numbers are significant, or I can say non-zero digits. Non-zero digits are significant. Yeah, let's say not whole numbers. All non-zero digits are significant. So 445 consists of four non-zero digits. Therefore, it has got three significant figures. The second rule that I want you to know is leading zeros. Leading zeros are not significant. When we say leading zeros, they are numbers that appear in front of a non-zero digit number. Let's say I say 004 has got one significant figure. If I can say 0.03, these zeros are at the beginning. So these zeros are not significant. The third rule that I want to talk about is zeros appearing in between non-zero digit numbers are significant. So if I were to write a number like 202, this zero in between adds significance because it's in between two non-zero digit numbers. Therefore, this one will have three significant figures. Zeros at the end are significant. So trailing zeros are significant. They are called trailing zeros or zeros at the end. They are all significant. Whether it has got a decimal point, whether it doesn't have a decimal point, they are significant. For example, if I can say 500, by the way, it depends. If I say 500 grams, this adding this unit ratio here makes this zero significant. But without units, no wonder we say every mathematical arithmetic, everything in math, everything in physics needs units. If you don't put units, this 500 won't have any significance. So this 500 will actually have one significant figure. But if I want to make it significant, I'll add units, 500 grams, 500 kwacha, 500 kg. So zeros at the end are significant if we have got units or if we have a decimal point after this non-zero digit. So if I say 500 grams, 500 grams has got three significant figures. Please pay attention today. You don't need very much distractions. We've started the war. Or if I say 500.00, all these zeros are going to be significant, trailing zeros, because of this decimal point there. So this will have one, two, three, four, five significant figures. So what did I say? The first rule, all non-zero digits are significant. The second rule, leading zeros, which are zeros at the beginning, are not significant. The third rule, zeros appearing in between two non-zero digit numbers are significant. The fourth rule is about trailing zeros, meaning zeros at the end. Zeros at the end are only significant if there is a numerical value, kg, kwacha, etc., or if there's a decimal point. So 500 grams has got three significant figures. 500 point, because of this decimal point, all these zeros at the end will be significant. So 500.00 has got five significant figures. So if we look at this digit here, 0.050200, what do we have? We've got a decimal point here, and we've got these leading zeros. So these leading zeros are not significant, but because of this decimal point here, these zeros at the end are going to be significant. Therefore, this number has got one, two, three, four, five significant figures. So our answer to this question here is option number C, which states five significant figures. Or we said put a cross, right, on the correct answer. So let me not circle because you end up circled in the answer in the exam also. So that's our answer there. All right. So let's move on to question number two. So for question number two, it's about density and flotation. It's a whole topic. We'll just say it's about density. So we all know the numerical formula for density, which you have to know. Physics is about formulas. You have to know one specific formula or a lot of specific formulas and how to apply them. So standard formula for density is mass over volume.
Over
So
volume.
let's read this question. Pay attention. Let's read this question. So we have a stone. By the way, when you say we have a stone, you have to understand that a stone is an irregular object. So for you to determine the density of an irregular object, there are two experiments that you can do. You can use a displacement can, or you can use a measuring cylinder to measure the volume of an irregular object. So here the question is telling you that we've got a stone there, a stone of mass 400 grams, so we do have the mass, is lowered into a measuring cylinder. So that's what I was saying. Why are you lowering this stone into a measuring cylinder? Because you cannot get the dimensions. It's an irregular object. So for example, if I were to have a cuboid like that, it would be easy for me to measure the volume. I'll just say, I'll look at the dimensions of length, breadth, and height, and say volume is equal to length times breadth times height. But if you have a stone like that, a stone is very irregular. You cannot determine the dimensions of this stone very easily. So you can't determine the volume. The only way you can determine the volume is if you lower this stone into you lower this stone into a measuring cylinder and you look at the water that has been displaced. So that's what the question is telling us here. I want you to understand, why are we lowering this stone into this measuring cylinder to obtain the value of volume. A measuring cylinder is an instrument that is used to measure volume. So they are saying it's lowered into a measuring cylinder and the water rises. The water initially, so the initial level of water was 300 cubic centimeters, and the water level after lowering this irregular object, this stone, the water level rose to 500 cubic centimeters. What is the density of the stone? That's what the question is asking for. So a good student would say, all right, density is equivalent to mass over volume. I do have the mass, which is 400 grams. What of the volume? The volume will be equal to the water displaced. How do we find that? We say volume final minus volume initial. So we have to measure the water difference here. So before the stone was put, it was 300 cubic centimeters. After adding the stone, the water rose to 500 cubic centimeters. Therefore, the volume will be V final minus V initial. The V final is 500 cubic centimeters minus the V initial, which is 300 cubic centimeters. If we subtract this, we're going to get 200 cubic centimeters. So we now have the value of volume. So we're going to say, all right, density is equivalent to mass over volume. So the mass is 400 grams over the volume, which we measured because of the water displaced, it became 200 cubic centimeters. Make sure you know your units. Density is either in standard SI units, which is kg per cubic meter, or in reduced SI units, which is grams per cubic centimeter. So you either have to have these two units to measure density. So here we have got grams, here we have got cubic centimeters, we are okay. You can't have kg and cubic meters in one equation, no. Meaning you have to convert this to uh, square cubic centimeters. So the units, you have to make sure the units are the same, either grams per cubic centimeter or standard SI unit, which is kg per cubic centimeter. So now we have the value of our mass and we now have the value of our volume. So all we have to do is divide. You get your calculator, because physics you're allowed to enter with a calculator. Once you divide that, you're going to get your value as 2 grams per cubic centimeter, which is this one here, option D, 2.00 grams per cubic centimeter. We're together.
Yes.
You really, really have to start revising. You have to solve as much as possible. So once I've solved this question here like this, it's going to come the exact same way, even in your exam. They won't change anything. The only thing they'll change is just the values, but the principle is going to remain the same. No wonder I keep on saying, watch this video, revise, know, try to understand, okay, the density of an irregular object, I have to calculate it like this, etc. So let's move on to question 3. It's saying A3 because it's in section A. So question 3, if you take a look at question 3, it's actually something interesting because it's something we've done. The previous, our last topic in physics before we started doing these past paper questions was motion graphs. And as you can see, this is a speed time graph because we have got speed in the y-axis and we also have time in the x-axis. And they are now saying the graph below shows the speed lighter. We are saying the graph below shows the speed of an athlete during a race. Then now the question goes further to say, what is the distance traveled by the athlete? So what is the distance traveled by the athlete? So in the previous lecture, I told you when you have a speed time graph, the area under the graph, the area under graph is going to represent the distance or the displacement. Because remember, like I said, for motion in a straight line, there is absolutely no difference between velocity and speed. Speed and velocity are exactly the same for motions in a straight line. Therefore, the area under this graph can represent both distance as well as displacement. So I want you to see this. We have got a variety of shapes here, but I don't want us to waste time. We actually have got 3 areas, but I'm going to summarize it into 2 shapes because I told you you have to know how your trapezium looks like. So your trapezium is going to look something like this. So this is how your trapezium is going to look like. Your trapezium is going to have a short side A. Is that a knock? Your trapezium is going to have a short side A, like so. And your trapezium is also going to have a long side B, and it's going to have a height. And I did say that the formula for trapezium is half, open brackets, the shorter side plus the longer side multiplied by height. But this shape here actually has 2 trapeziums. But one student will waste time and say, okay, we have the triangle here, shape 1. We have the rectangle here, shape 2. And we have got a trapezium here, shape 3. And they'll say, okay, we're going to use the first formula, half base times height plus length times breadth plus half open brackets a plus b multiplied by height. But this is time wasting. It's going to work, but it's sort of time wasting. So what we're going to do here, I'm going to show you the two trapeziums that I can see here so that you can also see them. So the first trapezium that I'm seeing here is this one. I'll highlight it in green. So this one here. So that's our first trapezium there. Then our second trapezium, I'll highlight it in purple. Or should I use blue? Which one should I use? Okay, I'll use blue. So that's our second trapezium right there. Do you see these trapeziums? Confirm. Do you see
Yes.
these two trapeziums?
Yes.
All right. So what we're going to say is that the distance will be, now we're going to say the two formulas of our trapeziums, half open brackets, a plus b close brackets height plus half open brackets, a plus b close brackets height. Remembering that a represents the shorter side of the trapezium, b represents the longer side of the trapezium, and this is the height of the trapezium. So let's look at our first trapezium here labeled in, which I've highlighted in green. So the distance from there to there is our shorter distance, which is A. And how do we get that that short distance? It's 14 minus 4, right? So we're going to say
Yes.
half open brackets, 14 minus 4 is 10.
Then
All right, excellent. Plus, this is the longer side. The longer side of this trapezium is from 0 to 14.
16.
It's from 0 to 14. So we're just going to say that's 14. And the height of this trapezium is this distance there, which is 5. Is that okay?
Yes.
So let's go to the other trapezium. We're going to say plus half open brackets. This one is sort of in reverse. The shorter side is from this side to this side, which is A, which is 5. So that distance from the base going upwards there, so it's 5. Then plus the longer side of this trapezium is this part here, which is from the base here going to this 10. So this is the longer side of this trapezium, so 5 plus 10, close brackets. The height now is the base, which is the distance from 16 minus 14. So 16 minus 14, which is 2. So these are our two trapeziums. The examiner has tricked you because they've placed the blue trapezium upside down. So they have just added the base on the x-axis. So therefore the height of this trapezium, or they have added the height on the x-axis. So the height of this trapezium is 16 minus 14, which is 2. Then the longer side is 10 centimeters from the ground level going up, which is 10 centimeters. Then the shorter side is from the ground going up to this part, which is 5 centimeters. So all we have to do now is get our calculator. You get your calculator and then you say 10 plus 14, you get 24. You multiply 24 by 5. After getting, you get 120. Then you divide 120 by 2 because you're halving it. So you're going to get your value, your answer as 60. Then you add it with, oh, where's my cursor? Okay. Then you add it with, you say 5 plus 10 equals, you multiply it by 2, then you divide, you get 30, then you divide it by 2 because you're half in it, you're going to get 15.
That's 16.
What are you getting?
16.
It's let's say 5 plus 10, you get 15, multiplied by 2, you get 30. 30 divided by 2, you have it, it's 15. You should you solve it properly, you get 15. Therefore, at the end of the day, you are going to say 15 plus 60, the two trapeziums. You are going to get 75.
75.
Excellent. Yeah, 75 meters. Answer 5 meters. So that's how you solve this question. And again, this same exact question is going to come. The principle, how you get to your answer. So how do you get to your answer? You just have to know two things. The first thing is that the area under a speed time graph will represent the distance or the displacement traveled. The second thing that you have to know is that what's the formula for area of a trapezium? Area of a trapezium is open brackets, the short side plus the longer side, close brackets multiplied by height, which is just half a plus b multiplied by height. Is that hard to remember?
No.
No, right? Exactly. But if you don't practice, trust me, you're going to forget. This will just look new. You'll be like, oh my goodness, what is this? I can't comprehend. Okay, so let's look at a question on free fall, but it's not necessarily a question of on free fall, but it's a question on free fall combined with work, energy, and power. So there are two topics that are combined, but it's work, energy, and power. I'm going to show you what I mean by that. So we have got a 4 kg brick. So a 4 kg brick is dropped from the top of a building whose height is 30 meters. Then the question says, what is the velocity with which it reaches the ground? So how do I know that this question of work, energy, and power and conservation of energy? uh, your equations don't work. Let's say things like V is equal to AT plus U, or S is equal to UT plus half AT squared. If you find that, all right, I haven't been given acceleration, I haven't been given the initial velocity, I haven't been given value of time, then the question points to work, energy, and power, and the conservation of energy. So let me draw this diagram for you here so that you can see it properly. So I'm going to draw this building here. What is it? A brick is it's a tall building. So that tall building there. So let me show you the energy conversions that are going to happen. At the very top of the building here, you are going to have maximum potential energy at its maximum, and the kinetic energy is going to be zero. There will be no kinetic energy. Kinetic energy is the energy of motion. So at the very top of this building, you are going to have potential energy maximum, kinetic energy zero. Then as this what's it's a brick, as this brick is falling, potential energy is going to be reducing, but it will be moving. So kinetic energy is going to be increasing. So it's going to be dropping, it will be moving very fast until it reaches halfway. When it reaches halfway, potential energy will be equal to kinetic energy. Then just before it hits the ground, kinetic energy will be at its maximum, and potential energy when it hits the ground will be zero. The total amount of energy, the energy that you start with and the energy that you end with, the kinetic energy that you end with, will be the same. That's the principle of conservation of energy. Energy is neither created or destroyed, it's just converted from one form to another. So this is the principle that you have to know in order for you to answer this question. So let's use this principle. Let me show you how this principle is used in action. So let's start off from here with this at the top of this building. We have maximum potential energy. How do you calculate potential energy? You have to know this formula. Potential energy is mass times gravity times height. You take gravity as 10. So the mass that we have is 4 kg times gravity, which you take as 10 multiplied by the height, which is 30. So let's look at the total energy that we start with here. You get your calculator and you say 4 times 10 times
40.
30. 10 times 10 times 30, you are going to get your answer as 1,200 joules. So here at maximum, we're going to have 1,200 joules. Halfway, we divide it by 2, we're going to get 600 joules. Then at the end, we'll have maximum kinetic energy back to 1,200 joules. So maximum kinetic energy is where we're going to find velocity, because kinetic energy is energy of motion. What is the velocity with which it reaches the ground? So with which it reaches the ground, it's using what type of energy? Kinetic energy. So we're going to say kinetic energy is equal to half mv squared. Know this formula. Let me rub the top part so that I can calculate properly, so that you see the flow properly of how the answer is going to flow once we start substituting. So you say kinetic energy is half mv squared. So the kinetic energy before it hits the ground will be the same as the potential energy because of the law of conservation of energy, which is 1,200, will be equivalent to half the mass we've been given. So the mass is 4 kg multiplied by the velocity squared that we want. We want velocity. So at the end of the day, we have to make v the subject of the formula. So we're going to say 1,200 is equivalent to 1 times 4 times v squared. It will be 4v squared over 2 over 1. If we divide this, we're going to get 2. So it's 1,200 is equivalent to 2v squared. We divide both sides by 2. We're going to get v squared as 600. To make v the subject of the formula, we'll square root both the left-hand side of the equation and the right-hand side of the equation. So our v will be equivalent to the square root of 600. So if you get your calculator and you say the square root of 600, you are going to get 24.49. 24.4948 something something. So you round it off to one decimal place or three significant figures, you're going to end up with 24.5 meters per second. Therefore, our answer here is B, which is 24.5 meters per second. Please go through these videos over and over again. They'll really make your life much better. So let's continue with the final 5 questions. Okay, so now we have got Newton's laws. A question on Newton's laws. You have to know Newton's laws of motion. Practically, Newton's laws is a topic in physics called dynamics. Dynamics in physics, we're explaining motion in terms of forces. So we're actually now knowing what's causing motion. And Newton's laws, we've got 3 laws of motion, which states that the first law of motion says an object will be at rest and it will continue at rest until an external force acts on it to change its motion. So if an object is moving at a constant speed of maybe 20 meters per second, or if it's at rest 0 meters per second, it will continue being at rest. Nothing is going to change it. Then Newton's second law is about resultant forces and unbalanced forces. So Newton's first law saying an object is at rest, it will continue being at rest until an unbalanced force acts on it to change its motion. So again, we're saying, all right, let's look at this one, Newton's second law. An unbalanced force acting on an object will produce an acceleration. That acceleration will be directly proportional to the force, but it will be inversely proportional to the mass of the object. So Newton's second law is summarized in the equation which says force is equivalent to mass times acceleration. So if we have got a force of 4 newtons in that direction, and we have got a force of 2 newtons uh, in the opposite direction. So this one's acting on this side, the other one is acting on the opposite direction. Our resultant force will be 4 newtons plus negative 2 newtons, and we're going to get 2 newtons to the right. But sometimes, if we have opposite forces having the same line of action, the resultant force is going to be 0. And if the resultant force is 0, the acceleration will be 0. If resultant force, so here you've seen we have got a resultant force. So this is the resultant force. So this object is going to move 2 newtons to the right. But what if we have a scenario where you have got 4 newtons acting this side, and you have got another 4 newtons acting on the other side? If you say 4 newtons plus negative 4 newtons in the opposite direction, if you expand, you're going to get 4 minus 4, which will be 0 newtons. This 0 newtons means resultant force. This force is equals to mass times acceleration is 0. And if it's 0, will there be acceleration? Acceleration will be 0. So no acceleration, meaning the object is moving at a constant speed. So using this same principle, let's go back to question 5 and try to answer this question. We are saying the diagram below shows an object moving with constant speed. So already we know one key thing here, we are saying constant speed, meaning resultant force, this F here is equivalent to 0. Meaning if force is equal to mass times acceleration, if this is equal to 0, meaning there is 0 acceleration. How is there 0 acceleration? How can there be a resultant force of 0? Is when the force acting to the left and the force acting to the right are equal in magnitude, but opposite in direction. So, when a force E, so it's at constant motion when this force, when a force E is at 30 Newton is applied. So we're applying 30 Newtons there. Again, constant motion means the resultant force is 0. So what is the value of the opposing force F? Definitely the opposing force, because of this part here, constant velocity, the opposing force has to be 30 newtons, such that when you add these two forces, you're going to have, where's my okay, you're going to have, I keep on losing my cursor, force E, which is 30 newtons, plus negative 30 newtons. This negative doesn't mean it's a negative. It means it's in the opposite direction. So force F is negative 30 newtons. It's 30 newtons acting in the opposite direction. So that's 30. So that will give us 30 minus 30, which will give us 0. So 0 resultant force means there is no acceleration. No acceleration means the object is moving at constant speed. And at what region of the speed time graph is the object moving at constant speed? At what region of the speed time graph is the object moving at constant speed when we have a straight line like that? A straight line here that is parallel to the x-axis. That's the y-axis. So this straight line here, it means the object is moving at constant speed. What do we mean when we say the object is moving at constant speed? When resultant force is 0, 30 newtons, 30 newtons, 30 plus negative 30, that will give you 30 minus 30, that will be 0 newtons. So this car is it a car or something? It's a car. So we are in this region here. Resultant force 0, meaning the object is moving with constant velocity. So our answer has to be C, which is 30 newtons. Are we together? It's physics. We've started really hardcore revision. If we were together, let's say from grade 10, if we moved together from grade 10 or even grade 11, grade 12, if we finished together, you would have been like a master at physics. But right now, we are in our rush hour phase. We want to pass the science exam, so we really have to cruise. And how do we cruise? You have to watch this video over and over, refer to past papers, go on the internet, go on YouTube, do some research, learn from other YouTube videos, just like that. Okay, so this is question 6. Question 6, students don't like this topic for some weird reason because it's on the turning effect of the force. It's an extension of dynamics, but you're explaining another type of motion, which is rotational motion. How can a force balance? So meaning some turning effect of a force. So turning effect of a force, turning effect, turning effects of a force is called the moment of the force. It's called moment. And for an object to be in equilibrium about a pivot, so if you have got an object like that, let's say maybe it's a ruler, and you have got a pivot there, and by the way, moment is the force applied multiplied by the perpendicular distance from the pivot. So that's your pivot right there. So that's our pivot. That's the perpendicular distance. So perpendicular, yeah, oh no, it's not. You're going to see the perpendicular distance soon. So if I add a force here upwards, so this is our line of action of the force. So the line of action of the force and the distance. So force times distance from the pivot. You see perpendicular means they'll meet at a 90-degree angle. So force times perpendicular distance will be the moment. So force there times perpendicular force 1, distance 1, that's perpendicular distance, and this is moving in a clockwise direction. But if I add, all right, clockwise direction, then if I add another force here, going downwards there like so, pulling it down. So this is force 2. And what's the perpendicular distance from the pivot? It's meeting at a 90-degree angle, anti-clockwise. So force 2 times distance are 2. So if this object here, if this ruler here that we've drawn here, for it to be balanced, the sum of the clockwise moment, force times distance, about this pivot has to be equal to the sum of anti-clockwise moment, force times distance about the same pivot. So sum of clockwise moment has to be equal to sum of anti-clockwise moment. So meaning F1 times distance 1, which is moment, has to be equal to force 2 times distance 2 about the period for this ruler to be balanced. And this principle is known as the principle of moment for objects that are balanced. The sum of clockwise moment has to be equivalent to the sum of anticlockwise moment. So let's look at this diagram here. So they are saying, let's now read the question. So a 600 Newton object is placed on a uniform bar that was balanced at its midpoint as shown in the diagram below. So we have the pivot there. The question is now saying which of the following will rebalance the beam? So which of the following will rebalance the beam? So here we are saying force 1 times distance 1. Force 1 is 600 newtons going down, 60 newtons going down, multiplied by distance 1, which is 30 centimeters. And what's the value of moment that we're getting, which is 60 times 30. 60 times 30, we're getting 1,800 Newton centimeter. That's the moment pulling it down. So for you to balance this one, your force 2 and distance 2, the value that you get after multiplying, if you put a force there, the value that you multiply should give you 1,800 in the opposite direction, which is anti-clockwise. So this is going clockwise. Oh, sorry, this is going. This is pulling it down this direction, which is anti-clockwise. No, is it anti-clockwise? Anyway, it doesn't matter. So the ones that are pulling it downwards like this, so this is pulling it downwards should be equivalent to the one that's pulling it this side so that the ruler can balance once more. So this moment here going in this direction, going in that direction, I've gotten lost. I don't know whether it's clockwise or anti-clockwise, but you get the picture. This one is going this side. I think it's so that's the pivot. So the pivot is going, I think it's anti-clockwise, and then this one, no, wait, it's clockwise, and then this one is anti-clockwise. Anyway, it doesn't matter. So these forces pulling it down. Oh yeah, let's use down and up. This force here pulling it down has to be equal to the force that's pulling it up so that the ruler can balance. And how did we get the moment there? We said this force here, force times perpendicular distance, it's meeting at a 90-degree angle there, is 1,800 newtons, because it's now 60 force times distance 30 has to be equal to force 2 times distance 2. So let's now start inspecting. So we've been given our values here. We've been given values here. So let's calculate the moments there. So we're going to say moment is force times force 2 times distance 2. So the first one here, 30 newtons times 30 newtons to the left of the pivot. So this is the left side, this is the right side. So let's multiply that 30 times 60. You are getting 1,800 newtons, which we want, but it shouldn't be to the left. So this one is wrong. Let's multiply 30 times 60. It's true. We're getting 1,800 newtons to the right of the pivot. So this one is the correct answer because 30 times 60 will give us 1,800 newtons. And 1,800 newtons, sum of clockwise moment is equal to sum of anti-clockwise moment, meaning this bar is going to balance up. 45 times 45, 45 times 45, you get 2,000, it won't balance. 90 times 20, 90 times 20, you get 1,800 newtons, but it's towards the left, it should be towards the right, it should be at this side. So our answer will become 30 newtons, B. Oh, where's my cursor? Okay, 30 newtons and 30 centimeters to the right of the pivot. So that's how you find the answer for this particular question here. Are we together?
Yes.
All right. Okay, so let's look at this question here. Oh, this question is funny because I see they're using, we have to actually use the vertical distance, not the horizontal distance. I'll show you just in a bit. So they are saying a motor is used to pull a 10 kg box along a 5-meter long incline to the top of the decline as shown above. So ignoring the forces of friction, determine the work done against gravity from the foot of the incline to the top of the incline. So work done against gravity, this is potential energy. So we just say potential energy is mass times gravity times height. So we're going to use this vertical distance here. That would be the height. So that's the height there, that this machine is pulling this box up. Would have used this here if it was work done against friction. So here we are calculating work done against friction, but the question says we're ignoring frictional forces. So this vertical distance, this horizontal distance, we're not going to use it in our formula. Work done against gravity is the height here, the vertical height. So knowing our formula, we'll just say potential energy mass times gravity times height. The mass is 10 times gravity, we're using 10. I said all the time the value of gravity has to be 10, whether they tell you or they don't tell you, multiplied by this vertical height, which is 4. So I think this will be 400 joules. 400 joules, which is option C there. Okay, let's move on to our last three questions. Question 3, 4, 5, whichever. 8, 9, and 10. Oh, interesting. Okay, interesting. Okay, so now we are saying a girl whose mass is 50 kg, so we've got a 50 kg girl, climbs a ladder of height 8 meters in 10 seconds. Now they are saying what power is developed by the girl. You have to know these formulas, by the way. You can't escape this. So the formula for power is defined as work done over time taken. And what work is she doing here? This girl is climbing up a ladder. And since she's climbing up a ladder, that's height. So there's the girl. Sorry for this drawing. So since she's climbing up a ladder, she's doing work. What type of work is she doing? She's doing work against gravity. So work done against gravity, because she's moving along a vertical height, is potential energy. So in this situation, in our power equation, the work done is potential energy. So work done is potential energy. So I'm going to say potential energy is mass times gravity times height. No wonder I said, so for this question, you have to know two things, two equations. Power is measured in watts, and it's work done over time taken. And you always have to figure out what type of work has been done. And in this scenario, the work that has been done is potential energy, because she's going upwards, she's climbing this ladder, and she has a mass of 50 times gravity, which is always 10, multiplied by the height of the ladder, which is 8. So all we have to do is get our calculator and say 50 times 10 times 8. 50 times 10 times 8, you're going to get 4,000 joules. 4,000 joules. So we substitute, the work done is 4,000 joules over the time taken, which is 10 seconds. Joules per second is a watt. So we cancel this, we cancel that. So that would be 400 joules per second or 400 watts. So our answer becomes B, like that. Okay, we are together.
Yes.
So please, when you get this video, make sure you revise it exactly the way I'm solving, the way I'm thinking, exactly the same in your tuition book. So let's move on to question 9. Are we together?
Yes.
All right. Let's move on to question 9, which is about its work, energy, and power, but it's also about efficiency. So we have got, interesting, a machine with a velocity ratio of 6. Interesting, velocity ratio. A machine with a velocity ratio of 6 requires an output energy of 800 joules to raise a load of 60 kg through a vertical distance of 6 meters. Find the efficiency of the machine. So again here, there's a formula. So given every time you see this velocity ratio, you have to use this formula. Efficiency, denoted by that scar n with a weird tail. Efficiency will be the mechanical advantage in a percentage, mechanical advantage in a percentage over the velocity ratio. Mechanical advantage over as a percentage over velocity ratio. So our mechanical advantage will be the load over the work, the energy output, the output energy. The load over the output energy, over the output energy. So again, what is the load? Remember the load, the output is 800 joules. The mechanical advantage multiplied by 100 because it's a percentage. Huh? So the mechanical advantage is a ratio, so it doesn't have units. So let's find the load. So 60 kg through a vertical distance, through a vertical distance of 1 meter. So 60 kg. Again, we have to calculate potential energy. So potential energy is mass times gravity times height. So the mass is 60 times the gravity, which is 10, times the vertical height, which is 1. We're getting a load of 600 joules. Now that we have the same units, we plug it in there, mechanical times 100 because it's a percentage. So mechanical advantage is load over the output multiplied by the 100. So the load, we've just calculated it as 600 joules. 600 joules, the joules cancel. So we will now say 600 divided by 800 multiplied by 100. 600 divided by 100, or divided by 800, sorry, divided by 800, you get 0.75. You multiply that by 100, you're going to get 75%. So our mechanical advantage, I always lose the case, our mechanical advantage becomes 75%. So we just substitute it in this equation. We say 75. By the way, a percentage is a number multiplied by, divided by 100. So this 75% is actually 75 over 100 divided by our mechanical advantage, which is 6. If we change this fraction, it will be 75 over 100 multiplied by 1 over 6. So we say 75 multiplied by 1 divided by 600. So we divide that by 600. Oh, what's this? Okay. We say, let's, oh, what am I doing? 75 divided by 100 multiplied by 6, sorry. So this is division. There's a division symbol there. So we're saying divided by 6, divided by 1/6. So we're saying 75 divided by 100, 75 divided by 100, which is 0.75. 0.75. Where am I losing it? Mechanical advantage over velocity ratio multiplied by 100. Oh, sorry. Okay. So 75%. 75 over 100 multiplied by velocity ratio. All right, it's fine. So, actually, let me just change this formula a bit. It has to be mechanical advantage over 100 because it's a fraction multiplied by the velocity ratio. Yeah, okay. Well, now, okay. So our mechanical advantage is 75%. So we'll say 75 over 100 multiplied by the velocity ratio, which is 6. Okay, well, now, okay. So we'll say 75 divided by 100, which will be 0.75 multiplied by 6. We're going to get our efficiency as 4.5. Let me re-explain this. Let me just re-explain this. Let me start it over. This 100 wasn't supposed to be there. I made a mistake on this formula. So the formula that you actually have to know is efficiency is mechanical advantage over 100 multiplied by the velocity ratio. So the mechanical advantage, we get it by load over energy output. We have to have the same units. So we said 60 times 10 times 1, which was our potential energy, as mass times gravity times height, we got 600 joules. So the formula wasn't supposed to have the 100 there. So 600 joules divided by 800 joules, our mechanical advantage became 600 divided by 800. We will get 0.75 as our mechanical advantage. So we substitute it there. So our mechanical advantage is 0.75 divided by 100 multiplied by 6. So if we divide this by 100 and multiply it by 6, oh, okay. Again, I'm making an error. The 100 is supposed to be there. Okay. Okay. Well, now, okay. So this 100 has to be there on this side of the equation. This last part. So this shouldn't be 0.75. It should be 75. So L, mechanical advantage, is equal to load over energy output times 100. So we're going to say potential energy mass times gravity times height, so 600 joules. So 600 divided by 800 multiplied by 100. So it will be 600 divided by 800, 0.75 times 100, you're getting 75. Okay. Okay, now this is okay. So our mechanical advantage is 75. So we just have to substitute in this formula, which says efficiency is mechanical advantage over 100 multiplied by velocity ratio. So our mechanical advantage is 75. So we're going to say 75 divided by 100, which is 0.75 multiplied by 6. We're going to get our answer as 4.5, which is what we have here. Right, let me just quickly explain this once more because we made errors. So the formula that we are supposed to use for mechanical advantage is load over the output energy multiplied by 100. So this is the formula that we have to use. Our output energy is 800 joules. Remember, mechanical advantage is a ratio. Since mechanical advantage is a ratio, we have to have the same units. So this load here, this load is doing work done against gravity. So we say mass times gravity times height. We'll say 60 kg times 10 times the vertical height of 1. We're going to get 600 joules as potential energy times 100. If we divide this, we're going to get 0.75 multiplied by 100, we'll get our mechanical advantage as 75. Then we substitute into this equation. Efficiency is mechanical advantage over 100 multiplied by our velocity ratio. Our mechanical advantage is 75 over 100 multiplied by the velocity ratio, which is 6 there, which is 6. So we'll say 75 divided by 100, we'll get 0.75 multiplied by 6, we'll get our answer as 4.5, which is C. Okay, please revise this. Things are getting very, very tricky. You have to be at the top of your revision game. You have to revise, revise, revise. Okay, so let's look at our last question here, which will just require a formula again that you have to memorize. So every time I say memorize a formula, write it down in your book, highlight it. So this question here just requires one formula. You can't run away from it. It's saying the diagram below shows the length of a mercury thread at ice and steam points. What will be the temperature if the length of the mercury thread is 25 millimeters? So here we are trying to calibrate our thermometer. Calibrate means to bring it back to a proper measurable level. And every time you're trying to calibrate a thermometer, you will need two things that you are supposed to have. You have to have your steam point, which is L100. Steam meaning it's above 100. It's a point where it's now steaming, which is slightly above 100 degrees Celsius. So L100 degrees Celsius. And our cold temperature, our ice point is L0, and you can find an unknown length here with a given length, which is L theta. So the temperature, the formula that you have to know, it's just one formula. Temperature is L100 degrees Celsius minus L0, which is so steam temperature minus cold temperature divided by this unknown length here, this L theta minus this ice point there, which is L0. So steam point minus ice point minus whatever length of the mercury thread that they'll give you. Here we've been given as 25 millimeters. And our L ice is 5 millimeters. And our L100 degrees Celsius is 15, right? 15. So all we have to do now is substitute. Our L100 degrees Celsius, which is our steam point, is 15, minus our L0, which is our ice point, is 5, over our L theta, the second reading that we've been given of the mercury thread is 25. The formula is multiplied by 100, minus our L0 again, which is 5, multiplied by 100. So all we have to do now here is just start dividing. This would be 10, this would be 20, multiplied by 100. So I'm going to say 10 divided by 20, 0.5, multiplied by 100, we're going to get our temperature as 50 degrees Celsius. So our answer here becomes D. What formula have we used? Temperature is the steam point, L100 degrees Celsius, minus the ice point, L0, over the new mercury reading thread, which is L theta, minus the ice point multiplied by 100. You have to know this formula. All right, so in our next physics lecture, you've seen that it requires me to explain quite a lot, literally topics, as I am trying to help you to answer this question. So I'm going to take it easy, we'll move slow, such that at the end of this physics paper 2020, you enter the exam room and then you say, I know all formulas, I know all principles, I can answer questions properly. So I'm going to send you the video after my class. I have a class at 17. Oh, I'm even late. I will see you tomorrow. Bye.
Okay.